This is an image of an erupting star in our universe. Quite lovely, isn't it? And this is another image of our universe. And so is this, and so is this. But how are we getting such beautiful and detailed images of space, you might be wondering? Well, it's actually been a long process of constantly perfecting our equipment, and it's what helped us go from this to this. So what exactly have engineers been doing to get sharper images, you ask? Well, that's what we're going to be discussing today on The Scientist's Guide to the Galaxy. I'm your host, Petra Radovanovic, and let's dive in. Well, the first thing we have to understand is how exactly a camera works. Well, all cameras have a light-sensitive sensor in them called a photodetector. Our cameras use CCDs, or charged coupled devices, but most commonly we use the newer version, which is a CMOS, a complementary metal oxide semiconductor. CMOS sensors have pixels in them, and each of those pixels is a photodiode, which is a simple kind of photodetector. Those photodetectors are what let us capture our images, and this is basically how they work. A photodetector is a device that converts light, or photons, into an electrical signal using a semiconductor material like silicone. It does this by the photoelectric effect, where the light that hits the photodetector excites an electron at the depletion zone and is then free to move, leaving behind a vacant spot called a hole. The electron then makes its way towards the positive terminal of an external circuit, and the hole makes its way towards the negative terminal of an external circuit. This movement causes an electric current to form, and that's what we detect as a signal to make our images with. In CMOS sensors, the last part is a bit different because they first allow the electrons to be collected as voltage, and then they read out the amount of voltage as a signal, and that's what they use to make the images with. So the imaging process is possible thanks to the photoelectric effect when the light hits the depletion zone, and that's exactly what engineers have been trying to perfect. They want to increase the efficiency of this process so as to capture more light, or photons, and therefore make better images, clearer and sharper. So how are they improving photoelectric efficiency? Well, first of all, they came up with this thing called 2D doping, and it's pretty cool. As we mentioned before, a silicone photodetector turns incoming photons into electron hole pairs, but ultraviolet photons are only absorbed within a few nanometers of the surface, so they don't penetrate very deeply, which is a problem. Because of this, we don't collect the light from the source because the outermost few nanometers of silicone tend to not capture light that well. This is due to the fact that the top layer of silicone doesn't have regular lattice structure anymore and has dangling bonds, or unpaired electrons that want to be filled. These dangling bonds create energy levels, otherwise known as trap states, where free electrons can fall in and get stuck instead of continuing their path as a free electron into the external circuit. This unfortunately means that an electron will not be able to produce an electric current, and so we will have no signal to make an image with. This is where 2D doping comes in. 2D doping is a technique that puts a thin, highly controlled sheet of dopant atoms on the surface of the silicone. This technique essentially paints a one-molecule thick electrical skin on top of the detector. This layer neutralizes the surface traps as it fills the unpaired electrons, and it also acts as a negatively charged electric field that helps direct the free electrons generated by the photoelectric effect back through the circuit instead of being trapped. This is because the dopant atoms and the electrons are both negatively charged, so they repel each other. So now, when a UV photon hits the surface, it has a much better chance of being collected. Engineers also came up with the atomic layer deposition technique, which I will let my colleague explain more in depth.
Hi, my name is Jacques, and I'm going to be talking about atomic layer deposition. So, even if the inside of the detector is perfectly designed, light still has to actually enter the silicon first. The problem is that when light hits bare silicon, around 30% of it just bounces off instead of actually being absorbed. And that's kind of a big issue when you're trying to detect faint light from a billion light years away. To fix this, scientists apply a super thin coating on top of that detector, only a few nanometers thick actually. This layer reduces reflection, filters out unwanted wavelengths, and also protects the detector from radiation and contamination in space, but it has to be extremely thin because if it's too thick, it can mess with how the photoelectric effect works and reduce sensitivity. This is where atomic layer deposition comes in. ALD is a very precise process that builds that coating one atomic layer at a time. It works through a series of carefully controlled, self-limiting chemical reactions, where first a gas is released into the reaction chamber where it reacts with the silicon surface and forms the first half of the layer. Then the chamber is flushed and a second gas is added. The second gas reacts with the first layer to complete one full atomic layer of the material. Now that's one cycle, and each cycle adds just one atomic layer, so by repeating it, scientists can create coatings that are exactly the thickness that they need, down to just a few nanometers and completely uniform across the surface. Now this kind of precision is pretty important in things like space telescopes and instruments that use UV or visible light. The coatings made through ALD can be tuned to let in just specific wavelengths like ultraviolet light that carries information about young stars, for example, while blocking others that could interfere with that data. So by using atomic layer deposition, scientists are able to make detectors that are more efficient, more durable, and better protected, which ultimately means sharper, clearer, and better images of space. Well, that's my section, so now I'm going to pass it over to Petra, who will finish the presentation.
Wonderful explanation. So atomic layer deposition basically prevents reflection, and it helps filter the unwanted wavelengths. Lastly, engineers came up with single photon sensitive CMOS image sensors, which are sensors that rely on very efficient photon to electron conversion and low noise readout. These sensors work by implementing a special kind of photodiode called a single photon avalanche diode, or a SPAD. In comparison with regular CMOS sensors that collect each photon using a pixel, convert that photon into voltage, and then store that voltage so that it can later be read as an electrical signal that we can use for imaging. SPAD technology has pixels that will only convert one photon into an electron, and then it will give that electron enough energy to run through the circuit and knock out other electrons on its way, making them free electrons. So it causes a domino effect, or an avalanche. That's why it's called an avalanche diode, because one electron can cause so many others to become free electrons. So it's a snowballing effect. This avalanche of electrons is then read out as a very strong electric pulse. In this way, SPAD allows a single photon to give the same large electrical signal readout that a regular CMOS sensor would only be capable of giving if it collected many photons. So SPAD basically allows us to get more out of every photon that's detected, and it gives us clearer images, like this one that was shot in almost complete darkness. Anyways, space observation is cool, and it's only getting better. That'll be all for today, and I'll see you on the next episode of The Scientist's Guide to the Galaxy. Bye!